And nowadays, in-memory caching has become an essential data center component and has been widely used by a lot of key players in the field. For example, Facebook uses their optimized Memcached and has a large-scale 2,000 node Memcached deployment in their local data center. While at the same time, Twitter uses Redis for performance optimization. In addition to that, cloud service providers have started providing automated in-memory caching as a service. For example, Amazon provides Elastic Cache service based on Memcached. Similarly, Google Cloud has their Memcached service as well. In fact, Airbnb is one of the popular apps that uses such kind of service. So in a typical deployment, database queries directly go downwards to the persistent database tier, which is really slow. So in order to improve the database query performance, we can have a dedicated in-memory caching tier that will be solely used for caching the database queries in a hierarchical storage architecture. Well, in-memory caching is so popular because it has several desirable features. It provides high-performance caching, enabling rates of millions of queries per second. It's also pretty easy to use and deploy. And in the cloud setting, it even supports elastic scale-out features. However, one plague that affects the overall resources efficiency of the memory caching system is the access load imbalance, where distribution of the load affects performance. To highlight this, we did one study where we measured the Memcached performance by varying the workload skewness from ideal balance to high imbalance associated with a pretty high zip-fan constant. To get a better idea of how a zip-fan constant affects the key popularity distribution or the workload skewness, let's take a look at this example shown in this inset. Here we see query distribution for different zip-fan constants. Basically, zip-fan constant of, say, 1.1 exhibit way more skewed key popularity distribution as compared to a modest zip-fan constant, say, a 0.5. So in this figure, the y-axis shows per client throughput in terms of thousands of queries per second. And the x-axis gives the workload skewness. So as you can see, by increasing the workload skewness, the throughput seen by the clients goes down by as much as 60%. Another key metric that users care about is the tail latency. The tail latency is crucial and is affected by the workload skewness as well. This is because a few cache servers that store the hotkeys might become the bottleneck of the overall performance of the memory caching system. To show this, we measured the corresponding tail latency as well. And we found it to be increased by more than 300%. Well, this is both bad news and good news. It's bad news because the performance is pretty sensitive to the workload skewness. On the other hand, it's also good news. This is because it demonstrates a great opportunity space for performance improvement of the memory caching system. So based on our study, there's an urgent need for a revisit to the memory cache design. To this end, we design and implement MBal, an in-memory object caching framework that comprehensively combines different techniques. MBal not only improves the single instance scale-up gains significantly, but also effectively mitigates the impact of load imbalance on performance. Now that I have given you an overview of our contribution, here is the outline of the rest of the talk. I will first explain how MBal and MBal cache load balancer work. Then I will show you how MBal load balancer behaves under different test scenarios. Finally, I will briefly present related work. Let's first look into the MBal cache design. Unlike the typical in-memory cache design, where all worker threads share a single in-memory data structure and use global logs for sync all operations. Within the MBal cache server, resources are horizontally partitioned across different worker threads, which means each worker thread maintains its own metadata and data. Such a partition is what we call a cachelet. A cachelet is basically a resource container that encapsulates resources such as CPU and memory. And more importantly, such a partitioning design eliminates most of the sync overhead, and it avoids lock contention on the critical path of both get and set operations. So how can a key be routed to a particular cachelet at the server side? This is done through a three-step mapping. When the clients issue a query to the cache cluster, it first computes the virtual node number using a hash function. The computed virtual node number is then mapped to a cachelet ID, which is embedded into the protocol header. The client library then sends out the request to the cache server. At the server side, the associated worker threads fetches the cachelet ID from the protocol header, and in turn locates the cachelet that the key belongs to. And next, I'm going to explain how MBal's cachelet design helps enable a better load balancing. Basically, the MBal load balancer adopts a multi-phase model, which utilizes three major different techniques. The first phase is key replication. This phase is inspired by the Sporn work that appeared in SOC 2013. However, MBal is different from this phase, from Sporn, in the sense that our system has multiple phases. And phase 1 key replication is only used for small ephemeral hotspots as a starting point. For more detail about this phase, please refer to our paper. The second phase, server local cachelet migration, where one or more cachelets can be migrated across different worker threads within the same server. In this example, as you can see, the orange cachelet is to be migrated from this orange worker threads to this green one in the middle. This phase is triggered when the hotspots are expanding and there is enough local headroom for saturating the load from the overloaded local worker thread in the same server. Phase 2 is coarse-grained at the per cachelet granularity. It uses a linear programming optimization model for guiding the local migrations. Phase 2 is also temporary, and it maintains migration states for a little while with the hope that the hotspots might be gone in a short period of time. The third phase, coordinated cachelet migration, where a central coordinator is involved in guiding the migrations. So this phase is triggered if both phase 1 and phase 2 cannot effectively mitigate the imbalance. And just like phase 2, it also uses a linear programming model for generating the migration schedule. However, unlike phase 1 or phase 2, phase 3 has permanent effect, which means the migration is stateless. Once the operation is finished, all state information regarding that migration operation will be permanently deleted from both within the MBal cache side and the MBal coordinator side. Another aspect of MBal design is that we have to inform clients about the key-to-cachelet mapping change. So in phase 2, this is done by clients are informed of the cachelet migration whenever the home worker threads receives any request regarding that just migrated cachelet. So for phase 3, this is done through a very simple protocol. Once the migration is finished, the source worker thread informs the central coordinator about the mapping change, while at the same time, clients periodically exchange the heartbeat messages with the central coordinator, and they would eventually see the mapping change. So that completes the three-phase load balancer design. Now let's look into the cost-benefit trade-offs of different phases employed by MBal. Phase 1 offers some benefit, but lies in the middle in terms of cost. Because it requires network transfer and must at least provide eventual consistency guarantee. Phase 2 is the most lightweight one, since there's no network transfer, no memory copy involved. So all is needed is just a pointer change in the local server. However, this phase is also necessary, as I will explain to you in the later slide in the evaluation part. Phase 3 is the most costly one, as it requires bulk data transfer through the network, which incurs the most significant overhead. So that completes the discussion about MBal design. Let's now see how MBal behaves under different test scenarios. In the evaluation part, first I'm going to show you how MBal's cachelet design improved the single instance scale-up gains on the local testbed. Then I'm going to show you how multi-phase load balancer behaves under different workload scenarios on a real-world 20-node EC2 cluster. In the first experiment, we run 100% get uniform workload from a local aggregated workload generator that ran on an 8-core 2-socket commodity server. Here we look at 4 different cases. MBal with no NUMA awareness, a Mercury, which is a highly optimized CPU cache-aware Memcached implementation, and the baseline case Memcached. This experiment is done without network just to show how the peak performance that each system can ever achieve. The y-axis of this figure is the throughput in terms of millions QPS, and the axis is the number of threads involved in each test. As we can see, MBal with no NUMA awareness can achieve 1.7 times more QPS than Memcached. And NUMA-aware MBal even further improves the performance by 15%. This is because Memcached contends for hash table bucket level logs, whereas MBal's horizontal partitioning design eliminates such kind of log contention. Next, we repeat the test with 100% set uniform workload under the same configuration. As we can see, Memcached cannot even scale up on a single server. A Mercury literally cannot scale up either, and it stops scaling at 4 threads. In contrast, MBal, the blue bars, show very good vertical scalability for write operations. Observe the orange and green bars for Mercury and Memcached respectively, whose performance is much lower. In fact, MBal can achieve 62 times more QPS as compared to the baseline case Memcached. This is because MBal avoids contention on global logs, which is used by Mercury and Memcached for sync the set operations. Besides this, we also test the complete cache system with a 10 gigabit Ethernet network attached. And we found that MBal was able to outperform both Mercury and Memcached by as much as 100%. So I encourage the interested readers to look at our paper for detail. Finally, we evaluate the MBal load balancer. We run a workload that consists of 3 sub-workloads on an EC2 20-node cluster. Each sub-workload ran for 200 seconds. Workload A is 100% read with ZFan key popularity distribution, which tries to mimic an application scenario where the user account status information is queried. Workload B is 95% read and 5% updates with hotspot distribution, and it tries to simulate a photo tagging workload in the real-world scenario. And workload C is write intensive with 50% updates, also with ZFan distribution. It tries to mimic a session store recording actions real-world workload. This timeline chart gives the 90th percentile read tail latency. The lower the better. The orange line is associated with Memcached performance, and also to get a better sense of how best we can achieve in terms of performance. We ran MBal under ideal balance, which provides a lower bound in terms of tail latency for performance comparison, as using the green line. As we observe, Memcached is not even able to sustain the write-intensive workload C. This red line is MBal performance with no load balancer support. Because of the fine-grained cachelet design, MBal is able to efficiently handle workload C. We also ran MBal with all load balancing phases enabled, as shown in this blue line. So let's see how MBal performs under different sub-workloads, one by one respectively. To zoom in, recall that workload A is 100% read with defend distribution. Hence, all three phases are triggered within this workload, and it can also successfully bring down the tail latency by as much as 35%. In workload B, 95% operations hit on 5% data, which kind of exhibit a semi-uniform key popularity distribution. As a result, phase 1 and phase 3 cannot effectively detect the workload skewness, whereas only phase 2 is triggered in this sub-workload B. Workload C is write-intensive with 50% updates. Hence, phase 1 is not effective at all for this sub-workload. The reason why is because the overhead of propagating write updates for key replication outweighs the benefit that it can bring in. Hence, a combination of phase 2 and phase 3 is triggered within this sub-workload, which can also bring down the latency by 23%. In summary, we see that MBal's cachelet design is able to improve the single instance scale-up gains by 2 times for get operations and 62 times for set operations respectively. And also, our end-to-end test on a real cloud cluster showed that MBal's multiphase load balancer is able to improve the throughput while at the same time reducing tail latency. And the side effect of this is that MBal is able to effectively improve span for the buck for the cloud tenants. MBal offers a promising solution. However, we are not alone in this field. Actually, MBal is inspired by a large body of research work. For instance, Mastery is a hybrid tree structured data store that appeared in Eurus's 2012. Similar to Mastery, MBal also uses cache-aware data structures for performance optimization. We also use the ideas from distributed hash table to migrate the data partitions for rebalancing the load. However, in MBal, we leverage integer linear programming just for access load rebalancing. Similarly, streaming analytics algorithm is a promising technique that can be used on a high-performance central proxy server for hotspot detection. Whereas MBal only uses such kind of central coordinator sparsely when all other phases cannot effectively mitigate the imbalance. In conclusion, I showed you how MBal leverages various different techniques for improving a memory cache performance. Specifically, within a single MBal cache server, the fine-grained partitioning design eliminates lock contention and enables good load balancing support. MBal also synthesizes 3 different load balancing techniques: key replication, server local cachelet migration, and coordinated cachelet migration to build a comprehensive multi-phase system that enables high efficiency in memory caching. With that, I conclude my talk, and I'm happy to take any questions. Thank you.
Questions? Hello, Malte Schwarzkopf from the University of Cambridge. So as you mentioned at the end of the talk, there's quite a lot of related work in terms of optimizing key value stores for multi-core, so Mica and mass tree and a couple of other things. Your biggest performance gain of 62x is on multi-core, but you also get the 2x performance gain when you run across the network. So have you compared against any of the multi-core stores? Because I'd be interested in knowing where you stand relative to those, right? I mean, obviously I realize that the goal of your system is to build a distributed system, and they are not doing that. So, but do you know roughly where you stand relative to these?
So actually, we compare the full cache system with Mercury and Memcached. We also conduct experiments on evaluating the comparison with, say, mass tree and Mica. It offers almost the same performance as mass tree, and we didn't put this in the paper.
Okay, thank you.
Hi, Tariq Turkestani from KAUST. So in the beginning of your talk, you showed in your motivation how accesses to some keys follow distribution, gamma distribution, where everything is skewed, right? How do you adapt to that during runtime? Do you have any tools to load balance? How do you load balance that?
So in order to perform the load balancing, we use a runtime analyzer to analyze the real-time workload skewness. And based on the severity of workload skewness, we conduct different load balancing techniques accordingly. For example, for the ephemeral hotspot, only for queue hotkeys, the key replication, the first phase, is the most effective phase. Whereas if the hotspots are expanding, it depends. If there is local enough headroom in the local server, phase 2 is triggered. And phase 3 is triggered if both phase 1 and phase 2 cannot effectively mitigate the imbalance.
Thank you.
Further questions?
Hey, I'm Joel Hirschman from ETH Zurich. So my question is how some of these, if you can elaborate a little bit of how this replicating a key has an effect on the consistency, or what is the model that you're approaching here? Do you only have eventual consistency in this cache, or is there any guarantee that you're breaking by doing these techniques? Thanks.
Okay, so this is a good question. So for phase 2, MBal can support both synchronous and asynchronous updates. For asynchronous updates, it improves performance by sacrificing some sort of consistency, because eventually, in the middle, before the final update reaches all the replicas, clients may see the stale information. And this is for phase 2. And for phase 3, it's completely okay, because for read updates, for read operations, there's no consistency issue at all. For updates, we treat this as a deny for the replication. And for the insert, we just simply return null to the cache server, because we are working on a caching layer. So so this is completely acceptable.
Okay, thank you. Let's thank the speaker again.
Thank you.